Hi guys, so today I'm going to show you another question. This question doesn't really have to do a lot with mathematical analysis or rigorous proofs, but this is a good problem solving question. It shows up quite often on my Facebook feed. They'll put up a random n by n grid, and then they'll ask you to compute the number of squares or the number of rectangles in that grid. So in this video, what I'm going to do is I'm going to show you exactly how to derive a general formula in order to compute the number of squares or the number of rectangles in any n by n grid. And in order to do so, we'll begin with a specific example in which I'll use a grid of size 5 by 5, and we'll compute the number of squares and rectangles in this 5 by 5 grid, and then see if we can generalize our results to any n by n grid. So at this stage, I'll ask you to pause the video and see if you can come up with a systematic way to compute the number of squares or the number of rectangles in this 5 by 5 grid, and see if you can also generalize your results to any n by n grid. So hopefully by now you've attempted this question on your own. I'm gonna begin with showing you exactly how to compute the number of squares. This is actually the harder of the two. Computing the number of rectangles is actually quite simple. So in order to compute the number of squares, I have copied this grid right here. So a systematic way to compute the number of squares would be to first identify the different types of squares that we have. Or more specifically, what I'm talking about is the different sizes of squares that we have. So in this case, we have 1 by 1 squares, we have 2 by 2 squares, we have 3 by 3 squares, 4 by 4 squares, and 5 by 5 squares. Now, if you'll notice, two of these are very easy to compute. 5 by 5 squares, well, there is exactly one, because, well, this is 5, this is 5. So this is 5 by 5, so there's exactly one 5 by 5 square. So let's just put one over here. So I have one 5 by 5 square. And while 1 by 1 is also very easy, there are exactly 5 1 by 1 squares in this section, and there are exactly 5 along this section. Sorry about that. 2, 3, 4, 5. So the total number of 1 by 1 squares have to be 5 times 5, which is 25. So we can put that right here. And you can actually verify that on your own as well, that there are indeed 25 1 by 1 squares. Now, the idea is to actually extend the same line of reasoning to computing the number of squares of other sizes as well. So let's look at 2 by 2 squares. So this is a 2 by 2 square. The idea is to compute exactly how many 2 by 2 squares do we have along each of the lengths of this 5 by 5 grid, and then multiply them in order to compute the number of 2 by 2 squares that we have in this entire grid. So this is one 2 by 2 square. I can move this square to the right by 1 unit, and I will get another 2 by 2 square. So that will look something like this. And then I can do this again once more. So that will give me a third 2 by 2 grid, and then a fourth. And I can do the same thing along the other length as well. So I will have, this is 1. So then I have 2, 3, and then 4. So there are exactly 4 2 by 2 squares along each of the lengths. So that means the total number of 2 by 2 squares must be 4 times 4, which is 16. And then you can repeat this process to 3 by 3 squares, and you'll figure out that there is a pretty nice pattern. The number of 3 by 3 squares along the length will be 3, along the other length will also be 3. So the total number of 3 by 3 squares are 3 times 3, which is 9. And well, the 4 by 4, if you go ahead and draw a 4 by 4 square, so this is a 4 by 4 square, you'll see that there are exactly two 4 by 4 squares along this length, and exactly 2 along this length, and 2 times 2 is 4, so you will get exactly 4 4 by 4 squares. Now, if you look at this right now, there's actually a pretty nice pattern that you should see. Um, that nice pattern is as follows. 25 is the same thing as 5 squared, 16 is the same thing as 4 squared, 9 is the same thing as 3 squared, and 4 is the same thing as 2 squared, and then finally I have 1 squared. So in general, what I got is that in a 5 by 5 grid, I had the total number of squares were 5 squared plus 4 squared plus 3 squared plus 2 squared plus 1 squared. And if you actually extend this line of reasoning to any n by n grid, you'll see that it actually holds. So in general, for an n by n grid, the number of squares is given by this n square plus n minus 1 square plus n minus 2 squared all the way up to 1 squared, which can be abbreviated and it can be written down as follows: the summation from I equals 1 to n of I squared. And we do have a very neat formula for this. This is the same thing as n times 2n plus 1 times n plus 1 divided by 6. So this has a separate proof, but the sum of the squares of the first n natural numbers is this right here. So it turns out that the number of squares in any n by n grid can actually be computed using this formula. So for example, let's say that I had a 6 by 6 grid and I wanted to compute the number of squares in that 6 by 6 grid. All I have to do at this stage is just sub in 6 into this formula. So instead of n, I'll put in 6. So I will get 6 times 2 times 6 plus 1 times 6 plus 1 divided by 6. These two 6's will just cancel out. I will get 6 2's as 12 plus 1 is 13. And then I will get 6 plus 1 is 7. And this is just 91. So in a 6 by 6 grid, for example, I will have exactly 91 squares. So the answer to this question, the number of squares in any n by n grid, is actually quite simple. It's just n times 2n plus 1 times n plus 1 divided by 6. Now, this other part right over here, how to compute the number of rectangles. Now, the issue is that if you actually use this method that I've just shown you right now, you're soon going to find out that the question becomes quite complicated and it becomes extremely long. The reason being is quite simple. If you are considering all the different types of rectangles in this, for example, in this 5 by 5 grid, you are soon going to realize that you will have to compute, for example, the number of 1 by 1 squares, 1 by 2 rectangles, 1 by 3 rectangles, 1 by 4, and then all the way up to, well, of course, just 1 by 5. Then you will have to do the same thing for 2 by 1, 2 by 2, and so on until you reach 5 by 5. And that isn't really a productive way to solve this question. Instead, the method that I'm going to show you involves using permutations and combinations. So there's actually another way that you can think about this question regarding how many rectangles are there in any arbitrary n by n grid. So once again, we're going to begin with an example of a grid, 5 by 5 grid. So it's a 5 by 5 grid. Now I'm going to create any arbitrary rectangle over here. So, I mean, let's just say that this is completely arbitrary. For example, let's say I draw these lines over here. And I'll draw this line over here. This one and this one. And now you can see that I actually have a rectangle right here. So there is a rectangle right there, and I have to figure out exactly how many rectangles I can create this way. Now, what I want you to notice is that in a 5 by 5 grid, there are exactly 6 horizontal lines and 6 vertical lines. So I'm going to create 6 horizontal and 6 vertical lines. So there you go. And then there is this line right here. There's this line right here. There is this line right here. And then there is finally this line right here. So there's 1, 2, 3, 4, 5, 6 lines, 6 horizontal lines, and then 1, 2, 3, 4, 5, 6 vertical lines. And the idea is that since a rectangle has 4 sides, I need to pick any 2 lines, any 2 horizontal lines, and any 2 vertical lines. So that is equivalent to saying how many different ways are there for me to pick 2 horizontal lines from the 6 horizontal lines that I have. And if you know combinations, then you know that the answer to this question is just 6C2. This is a mathematical operation that will tell you how many different ways are there for you to pick 2 lines from a total of 6 lines. And of course, it's the same thing along, it is the idea is the same for vertical lines as well. I need to pick any 2 lines from a set of 6 vertical lines. And the formula to do that is also 6C2. And in order to figure out the total number of combinations that are total number of possible combinations, all I need to do is I need to multiply these two with each other. So it's 6C2 multiplied by 6C2, and that will give you the answer. That is the answer. So there is a way to expand this. You can write this out as 6 factorial divided by 6 minus 2 factorial times 2 factorial multiplied by 6 factorial divided by 6 minus 2 factorial times 2 factorial. And then well, I'm going to simplify this one right here. So you're going to get 6 factorial divided by 4 factorial times 2 factorial squared, which is the same thing as, so 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. And well, okay, I'll just write it out over here. 4 times 3 times 2 times 1. 4 factorial is 4 times 3 times 2 times 1. And then 2 factorial is just 2 times 1. I have to square this. You'll see that this 4 times 3 times 2 times 1 will cancel with this. I can also simplify right here. So the answer is just 15 squared, which is 225. So in other words, in a 5 by 5 grid, there are exactly 225 rectangles. Now, of course, we can also generalize this result. The idea is that in any n by n grid, you have n plus 1 horizontal lines and n plus 1 vertical lines. So what you can say is that in general, for an n by n grid, the total number of rectangles that can be created can be given by n plus 1, where n is the size of the grid, n plus 1 C2 multiplied by n plus 1 C2, which can also be written as n plus 1 C2 squared. Now I'm gonna leave you with this one thought. If you actually go about solving this question regarding the number of rectangles in an n by n grid using this other method that we used right here, what you get is that the number of rectangles in any n by n grid can also be written as n times n plus 1 divided by 2 squared. So this exercise that I'm going to leave for you is to actually prove that these two expressions are equivalent. Both of those are equal to each other for any positive value of n. Yep, and that's it. I hope you enjoyed the video, and yep, I'll see you in the next video.